Hello and welcome to our lab on free fall acceleration. Free fall is defined as the acceleration experienced by an object when the only force acting on it is the gravitational pull of the Earth. And now sometimes, even some air resistance, we still refer to that as free fall. And so we're going to drop this shuttle. I have a little shuttle here. We're going to drop it. It's going to fall under gravity with some frictional resistance and some air resistance, so it's not exactly free fall. But let me show you how this works. This shuttle has a metal tip and it's attached to this electromagnet. When I cut the power to the electromagnet, the shuttle will fall. Now at the same time, in order for me to get some meaningful data from this falling shuttle, I have this apparatus attached to a high voltage, around 15,000 volts, power supply. Now behind the shuttle is a wire going the length of the drop, and in front of the shuttle is another wire going the length of the drop. And when I begin to spark, cause sparks to fly, electricity will pass from one wire through the shuttle and to the other wire on its way from the live wire to the ground wire behind the shuttle. And this sparking occurs every 60th of a second. So 60 times a second, this generates a spark. Now, still nothing would happen. We'd have no data, but I've put a strip of white paper between the shuttle and the grounded wire. And so when a spark goes from the live wire in front through the shuttle to the grounded wire, it must pass through the paper along the way. And when that happens, it burns a tiny hole in the paper. Now as the shuttle falls, theory predicts that it gets faster and faster under the constant acceleration due to the gravitational pull of the Earth. In that case, we would predict that the spaces between the burned dots in the paper are going to increase with time, because even though this is sparking at 60 times per second, a very even interval, the shuttle is falling faster and faster. So for that even time interval, it falls a little farther each time because it's moving faster. And so when we get finished, you'll have a strip of paper, and on it are a succession of dots. And sure enough, you should notice that the dots are closer together near the top, and they get farther apart at the bottom. Now, as we saw in an earlier lab, there is a kinematic equation that relates the position of an object with time when it's under a constant acceleration, for example, due to free fall. And so what you're going to do is measure the distances between each dot, or every other dot, which would be 1/30th of a second, and you're going to plot that data, and then you're going to check to see if it in fact does fit this quadratic mathematical model which is predicted for an object in free fall. And if it does, then from the parameters of that curve fit of the data, once you put it into Logger Pro, you should be able to determine what the acceleration parameter is. And if this truly is an object in free fall and our data is good, that acceleration parameter should be close to 9.8, which is the value of acceleration of a body in free fall near the surface of the Earth. More specifically in our lab, we show you why we use a value 9.7953. It's a little more accurate depending on our altitude and our latitude, and it has more significant figures. So that's the value that we're going to compare our graphically determined value of free fall to. So here it goes. I've got my spark set up. I can see the spark happening up here. When I release, the shuttle falls down under gravity, and all the way down we have a steadily increasing series of burn marks. Okay, welcome to part 2 of free fall. Now this part involves a meter stick, a golf ball, and a video camera. Now the way that we're going to examine the free fall motion of that golf ball is using a video camera. Now this camera is attached to the computer using a USB cable, and it interfaces with Logger Pro, our graphing software. Now we're going to put this camera out at a distance to where it can see the entire drop. I'm going to do this on the tabletop, but you should do it out in the hallway. Now that camera has no way of knowing how far away I am from it. It doesn't have the distance detection capability of the motion sensor, so I have to tell it. I have to say, this stick is the length of 1 meter. Okay? And there's some problems with that. First of all, the bottom of this stick is closer to the camera than the top of the stick. So I'm going to get some error there. What I really want to do is have the camera farther away and position this meter stick so that the center of the stick is the closest to the camera. I'm still going to get some curvation effects due to the fact that the ends of the stick are further from the camera than the center, but it's something I'll just have to deal with. Talk about it in your error analysis. Alright, but once I've set that up, I'm going to open up Logger Pro, and there's a tutorial for you to do that sort of teaches you how to do a video analysis of frame by frame motion in Logger Pro. Do that tutorial. But when you come back to this, you're going to be dropping a ball in the same plane as the reference meter stick, and in frame by frame, you'll be analyzing the drop of the ball. Now, theory predicts that as the ball drops, it gets faster and faster, and so in each frame, the ball should be further and further along its path. And if it bounces, it'll continue through the bounce, and you should notice that at the top of the bounce, it's moving slower. Near the bottom of the bounce, it's moving more quickly. And so as this graphs in Logger Pro, based on the tutorial you will have already done, you should be able to fit your video frame by frame analysis with a quadratic function, and from that function determine the free fall acceleration of this ball, which should compare, using percent error, to the value of free fall acceleration here in Boone, North Carolina.